Hello and welcome to another episode of Physics Lab. Today we're going over magnets, specifically magnetic dipoles, as along with ways on how to simulate them at different locations. Okay, so for the observed values, as you can see with this graph, we have not a linear relationship. It looks like a linear relationship. That's because we're using the natural log, which in this case indicates that it's some kind of polynomial relationship. And as you can see, as r, or the natural log of r, gets higher, then the magnetic field gets lower, which is also true for the standard version of it. And for the calculations and observations, it was relatively simple. We took the magnitude of the net magnetic field at different distances from the magnet. And so while we were testing it, there was always some kind of fuzz or variation in the magnetic field. However, when I took it again just outside of the laboratory setting, it was considerably more stable and calm. So, that could have messed with the results a little bit. And then we plugged a lot of that into Excel just to have it crunch the numbers for us. Now for the computation, it was kind of followed a lot of the same calculations, but with some key differences. For the field, we got 4.21 times 10 to the negative 5 Teslas. And we always assumed that the distance is very far from the dipole, that the z component is nothing. That's just perfectly in line with the magnet, and naturally that the magnetic dipole is the only thing there. So in comparison, the off-axis magnitude is very close to the net off-axis for the measured values. It was 1.4 e to the negative 4 computed versus 1.7 e to the negative 4 computed. But for the other magnitudes, the other values, they were considerably further apart. So, obviously there was something wrong with either our measurements or with our calculations. And some potential source of error is that the measurement was performed by ruler, so it wasn't perfect. We tried to iron that out by taking multiple measurements and averaging them, but that still introduces some error. And then also is that the computation neglects any kind of outside sources. So we tried to account for the magnetic north, the magnetic field of Earth, but that isn't the only magnetic source there. Since we were in a lab, there were many other magnets, many other electronics that could have been interfering and messing up the numbers. Now, what if we didn't compensate for magnetic north? Then that would have changed. Well, it depends on how much it changed. It definitely would have either increased or decreased the apparent strength of the bar magnet that we had. But without knowing the exact angle, it's difficult to say by how much it would have. Although it would have been some trigonometric constant, sine, cosine, something like that. And if we stuck the two magnets together, then the magnetic field would be approximately twice as strong as the single magnet. Because and because of that, the magnetic dipole moment would be twice as large. And kind of as a way to think about this, imagine if the two magnets didn't interact with each other at all. They had no attraction or repulsion, and we just kind of placed them next to each other. Then the net magnetic field on our observation location would double. And since magnetic fields don't interfere with one another, then this same applies when they stick with each other. And in conclusion, magnetic dipoles follow a dipole pattern, and that taking the observations will yield a general insight into the shape and magnitude of what is happening with the magnetic field. Thank you, and hope you tune in for another episode.